We want to find the curvature of the curve given by the vectored valued function r of t at the point when t equals 2. The curvature at a point measures how sharply the curve bends or how quickly it changes direction. As an example, the curvature of a line is 0 since a line does not bend or change direction, and the curvature of a circle is equal to the reciprocal of the radius, or 1 divided by r. More formally, the curvature measures how quickly the direction of the unit tangent changes with respect to a change in arc length s. So we can define curvature k as we see here, but notice how this requires the unit tangent vector to be defined in terms of s arc length, so we won't be using this formula. We'll be using one of these formulas here. More specifically, we'll be using this alternative formula for curvature, where we have the magnitude of the cross product of r prime of 2 crossed with r double prime of 2 divided by the magnitude of r prime of 2 cubed. Now before we do this, let's look at this graphically. Here's a graph of our space curve, and notice how this circle here would be called the circle of curvature at this point here on the curve, and therefore the curvature of the space curve is equal to 1 divided by the radius of this circle. The center of the circle can also be called the center of curvature. And we're trying to find the curvature when t equals 2. The reciprocal of this radius would be the curvature when t equals 1/2. So notice when t equals 2, here, notice how the circle is extremely large, which means the radius is large, and since the curvature is the reciprocal of the radius, we should expect a very small curvature when t equals 2. If I zoom out, we'll eventually see the circle of curvature. So here we finally see it, but we've zoomed way out, and therefore this radius is extremely large, again meaning the curvature will be extremely small. So we'll begin by determining our first and second derivatives of r of t, and then evaluate those vector functions at t equals 2. So r prime of t would have an x component of -5, the derivative of -5t with respect to t, a y component of 6t squared, the derivative of 2t to the third with respect to t, and a z component of 12t to the third, which is a derivative of 3t to the fourth with respect to t. Now let's go ahead and evaluate this at t equals 2. So we have r prime of 2. So we'd have an x component of -5, a y component of 6 times 2 squared, and a z component of 12 times 2 to the third. So simplifying, we'd have -5, comma, 6 times 4 is 24, and 12 times 8 would be 96. So we just found r prime of 2. Now we'll find r double prime of 2, then find the cross product, then find the magnitude, then divide by the magnitude of r prime of 2 cubed. So r double prime of t would be equal to the derivative of r prime of t. So we'd have an x component of 0, a y component of 12t, and a z component of 36t squared. So now r double prime of 2, we'll substitute 2 for t. So we have an x component of 0, a y component of 12 times 2, and a z component of 36 times 2 squared. So we have an x component of 0, a y component of 24, and a z component of 36 times 4, which is equal to 144. So now we'll find the cross product of these two vectors. So we'll have r prime of 2 crossed with r double prime of 2. And we'll go ahead and find this cross product using a 3×3 determinant and expansion by minors. So we'll have a 3×3 determinant, where the first row would be the I vector, the j vector, and the k vector. The second row would be r prime of 2, which is -5, 24, 96. And the third row would be r double prime of 2, which is 0, 24, and 144. And now using expansion by minors, we'll have a 2 by 2 determinant times vector I minus a 2 by 2 determinant times vector j plus a 2 by 2 determinant times vector k. Remember, whenever we set up the expansion by minors method to evaluate a 3 by 3 determinant, and we use this first row, it'll always be a positive, minus, and then plus. And now to determine the elements in this first determinant, we eliminate the row and column of the I vector, so the first row and the first column, which leaves us with the elements 24, 96, 24, and 144. And now for the second 2 by 2 determinant, eliminate the row and column of vector j. So now we eliminate the first row and the second column. So we have -5, 96, 0, and 144. And finally, for this third 2 by 2 determinant, we'll eliminate row 1, column 3. So we have -5, 24, 0, and 24. So simplifying here, I'll go ahead and let you check this. We'd have 1,152 times vector I plus 720 times vector j, and then minus 120 times vector k. Just for review, to find these 2 by 2 determinants, we would find this product minus this product for each 2 by 2 determinant. So in component form, we'd have an x component of 1,152, a y component of 720, and a z component of -120. So now we know that r prime of 2 crossed with r double prime of 2, and we also found earlier that r prime of 2 has components -5, 24, 96. And now we can go ahead and find the curvature. The curvature k is equal to the magnitude of our cross product. So we'd have the square root of 1,152 squared plus 720 squared plus -120 squared divided by the magnitude of r prime of 2 cubed. So we'd have this cubed, and then we have the square root of -5 squared plus 24 squared plus 96 squared. And now we'll go to the calculator to approximate this value. Of course, you do want to be careful entering this in. So we'll have a numerator in parentheses. So we'll have the square root of 1,152 squared plus 720 squared plus -120 squared. Notice how because this is negative, we do have to have this in parentheses. So that's our numerator. So I'll press right arrow, close parenthesis, divided by our denominator. So we'll have another open parenthesis, and then the square root of, in parentheses, -5 squared plus 24 squared plus 96 squared. Right arrow, close the parentheses here, and then raise this to the third power. So caret 3 and enter. So to 4 decimal places, the curvature is approximately 0.0014. So just as we expected, notice how the curvature is very small because the radius of the circle of curvature is very large. So here we have the curvature of our curve at the point when t equals 2 is approximately 0.0014. So if we go back to our graph just for a moment, this curvature is equal to the reciprocal of the radius of the circle of curvature, seen here. I hope you found this helpful.